Hello.
Hi, I am Sumegha. Today I'll be talking about our paper Network Coding in Undirected Graphs is either very helpful or not helpful at all. This is joint work with Mark Braverman and R.L. Schwartzman. Let me start with reminding you the problem of multi-commodity flow. Here you are given a graph G and along with a set of commodities and a capacity function C that assigns a positive capacity to every edge in the graph. And each commodity has a source node and a sink node, and transfer of commodity from source to sink can be thought of as a flow on a connecting path. We want to send flows for each commodity simultaneously at a rate r such that the total flow through any edge is upper bounded by its capacity. The multi-commodity flow rate is the maximum such r possible, and we denote it by MCF in the remaining talk. So what if the commodities are bits? What the flows is essentially doing is it brings it at any intermediate node, it just reshuffles the bit and send on the outgoing edges. But because the commodities are now bits, can we do some re-encodings at the intermediate nodes and get a better information rate? This is the natural question in the field of network coding. And this network coding was first introduced in 2000 by Elswede et al. So in the field of network coding, the problem is each source has some message bits that it wants to communicate to the corresponding sink. At any intermediate node, the node sends a bit on the outgoing edge, which is a function of the incoming edges. And the coding should be such that every sink node should be able to decode the message the source was trying to send it using the information in the incoming edges at the node. Finally, we also want that the entropy of any edge should be bounded by the capacity, where the edge is thought of as a random variable when we have a uniform distribution over the message state. So in multi-commodity flow setting, it makes sense to think about fractional flows. But in network coding setting, as we are sending bits, half a bit doesn't make sense. Thus, we define the network coding rate as the limit of the maximum communication rate of a graph GB, where GB is the graph obtained by multiplying all the capacities by B. So our question was, can these bit tricks give us better information rate than simple flows? The answer is yes in directed graphs. We can see this by this cute example. So here a path from source 1 to sink 1 passes through this blue edge, and there is only one such path from between source 1 and sink 1. The same is true for source 2 and sink 2. So if this blue edge has capacity 1, then this becomes the bottleneck for the multi-commodity flow rate, giving us an upper bound of half on the rate. But in network coding, this intermediate node can send x1 or x2 on this blue edge, and the sink can decode x1, and the sink 1 can decode x1 using x1 or x2 and x2. Thus, this gives a rate of network coding rate of 1 and NC by MCF gap of 2. These papers by Kleinberg et al. Shows that this gap can be made as large as order size of G. So now, what do we know about we don't know much about the NC by MCF gap for the undirected graphs. The first attempt was to bound the network coding rate by the sparsity of the undirected graph. So sparsity of a cut, we consider a cut between U and V minus U. The sparsity of this cut is the capacity of the cut divided by the number of sourcing pairs it separates. So for example, the sparsity of this cut is 5. Then the sparsity of the entire graph is the minimum of the sparsity over all these cuts. Now we know it is clear that the network coding rate is an upper bound on the MCF rate, because in MCF you are just doing the function is just the permutation at every node. And also it is easy to see that the sparsity is an upper bound on the network coding rate for undirected graphs, because even if we shrink all the vertices in U to a single vertex, we get that these orange edges should contain all the information about the sourcing pairs it separates. Thus, the sparsity of the graph should be an upper bound on the network coding rate. In 1999, Leighton Rao proved that the maximum gap between sparsity and the multi-commutative flow rate can be order log G, and this is actually attained by expander graphs. So thus, this sparsity bound is a loose bound on the network coding rate. This also gives us that the maximum gap between network coding and MCF can be order log G, whereas in directed graphs it could be order G. In fact, in 2004, Lee and Lee conjectured that multi-commutative flow rate is equal to network coding rate for all undirected graphs, that is, coding gives no advantage. While we do not prove or disprove the conjecture in our paper, we prove that either the conjecture is true, which would be huge, or it must be nearly completely false. That is, the network coding and undirected graphs give almost the optimal advantage. So our main theorem states that given a graph G that achieves a gap of 1 plus epsilon, we can construct an infinite family of graphs that achieve a gap of order log G, size of G to the C, where C is some constant less than 1. So the building block of our theorem is a graph tensor construction that takes two graphs G1 and G2 with gap 1 plus with gaps and construct a new graph G with a gap equal to the product of the previous two gaps while keeping a check on the size of G. And we apply this construction repeatedly to get our main theorem. Okay, let's delve deeper into the graph tensor construction. Just for illustration, assume that these are the two graphs G1 and G2 that exhibit a network coding by MCF gap. Note that for this graph G2, if we think of an information channel at the endpoints of S2 having the endpoints of a sourcing pair, then this channel has a channel capacity more in network coding than under simple flows. Now, if we take this sourcing pair and replace this edge with this sourcing pair like this, then we would see that the effective capacity under network coding for this edge would be greater than that under simple flows. In the graph tensor construction, we keep the sourcing pairs of graph G1 and the edges of graph G2. But here, however, for G2 there is a gap only when all the sourcing pairs send information simultaneously. So we need to use the other sourcing pairs of G2, and to do that we add multiple copies of G1 in our graph, such that each sourcing pair in a copy of G2 replaces an edge in different copies of G1. We can see that using this picture. So the orange graph is the first copy of G1. Its edges are replaced by the second sourcing pairs of copies of G2, and the green graph is the second copy of G1, whose sourcing pairs are replaced by the first sourcing pairs of the copies of G2. Now here we could see that we could assume that the effective capacity seen by all the copies of G1 would be more under network coding than under simple flows, and as information grows linearly with the capacity, we could expect that the gaps would also multiply. But however, this is not our final tensor because there are still some complications which we will address in the upcoming slides. Before that, to say something about the gap between network coding and multi-commutative flow rate for the graph G, we lower bound the network coding rate and upper bound the MCF rate. Lower bounding the network coding rate for the new graph is easy because we just construct a network coding solution for G with the rate equal to the product of the previous rates. To do this, we compose the network coding solution of G1 on that of G2, or network coding solution of G2 on that of G1. The hard part is upper bounding the multi-commodity flow rate. As you all know, the maximizing the multi-commodity flow rate can be written as a linear program. So we consider the dual LP of this linear program. Any dual solution will give an objective value which is an upper bound on the multi-commodity flow rate. So we start with the dual solutions D1 and D2 for the graphs G1 and G2, and construct a new dual solution D with the objective value equal to the product of the dual solutions, product of the objective values of the previous dual solutions. Okay, what is this dual solution? Any dual solution assigns costs to each edge, cost per unit capacity to each edge. So the objective then becomes the maximum revenue that can be gained from this graph. And this LSITI denotes the shortest distance between the ith sourcing pair under this cost metric. So for sending 1 unit of flow, any sender would need to give this much amount of money to this much amount of money, and thus for sending 1 unit of flow across all sourcing pairs, this is the cost incurred. So it is clear to see that the maximum total revenue possible divided by this quantity would be an upper bound on the network coding rate, on the multi-commodity flow rate. And thus this is the dual solution. The dual solution cares about two things: the weight, the cost it associates to each edge, and the shortest distances between any sourcing pair. So the costs easily tensorize in the sense that we can take the new cost to be the product of the cost in the previous two dual solutions. But the question is, do the shortest paths also tensorize? The answer is not yet. So as you can see, ideally we would want that this purple path should be the shortest path in the new graph G between this sourcing pair, because in some sense this is the product of the shortest distances in the previous graphs. But because we added these new connections through the second graph of G1, through the second copy of G1, after going here, the path can jump directly to this source of the node of a copy of G2 and construct a red path that makes distances shorter than expected. So these are the cheating paths which do not correspond to product of the shortest paths in the previous graphs, and we would ideally want to avoid these cheating paths, so that we can actually say something about the upper bound on the multi-commodity flow rate. So a good part of our construction goes into avoiding these cheating paths. As you will see, as you saw, cheating path traverses through different copies of G1 using the connections through copies of G2. And if we increase the number of hops every path has to take before it reaches the same copy of G1, then we could say that every cheating path has a very long length. This is exactly what we do. To do this, we think of our construction as a bipartite graph where the left side represents the copies of G1 and the right side represents the copies of G2. There is an edge between ij in bipartite graph B if an edge in ith copy of G1 is replaced by a sourcing pair in jth copy of G2. So these are the bipartite graphs on which we base our graph tensor construction. to achieve the fact that there should be large number of hops for every path before it returns to the same copy of G1, we require that these bipartite graphs should be high girth, and this requirement of B being high girth actually gives us a large but bounded blow up in the size of the final graph tensor G. And if we didn't have this requirement, then it is interesting to note that we would actually prove the conjecture by amplifying the gap above order log G. So to wrap up, finally our graph tensor construction starts with a graph G with a gap with size this and a gap, and creates another graph G dash with size this and a gap of 1 plus epsilon square. We use this theorem repeatedly, that is, in every iteration we apply this theorem to the graph itself, to the graph obtained in the last iteration, and finally get the gap growth as order log of size of G to the C1, where C1 is a constant. So finally, there are two big open problems in this area. The first open problem is for undirected graphs, which is proving or disproving the Lee and Lee conjecture. We don't know the truth of this. We don't know the truth of the conjecture even for linear codes, where linear codes are restricted to coding schemes where at any intermediate node the function is linear. And the second big open problem is for directed graphs, where people don't know how to compute the optimal network coding rate for directed graphs. Okay, thanks.
What exactly is the dependence on epsilon? So we start with something that has an advantage 1 plus epsilon. Does epsilon play any part in the final log?
It plays in the log. It comes in the C1, that's the constant C. It's like log of 1 plus epsilon divided by log D, where D is the diameter of the starting graph.
What's your personal belief about the Lee-Lee conjecture?
It keeps shifting, but I believe it should be true for at least linear codes.
Since publishing the paper, is there any sense in trying to improve the constants you want, or to see?
No, because I don't think we can get around the fact that the constant there would be at least like 1 plus epsilon divided by D, where D is the diameter of the starting graph. So it depends on this constant depends on the starting graph, and as we don't have any knowledge about these graphs that exhibit a gap, so I don't think we can improve the constant.